So what we're going to do is talk about the formula. This is called the one sample Z interval from U. This is the one we introduced last time. So we'll go over the formula and the assumptions and then look at a handful of examples. So the formula we had up there before was this x bar plus or minus. Last time I had a 1.96 here. This time I've got something called a ZCV. So I'm calling that, the ZCV is just my way of saying a Z critical value. And a critical value just comes off a table, like your Z table or something like that. So when you see a Z critical value, or later on we're going to have like T critical values and all sorts of other things. When you see a critical value, that just means something that comes off of one of these tables. Okay. So the formula, you take x bar plus or minus some Z critical value times sigma divided by the square root of that. The assumptions, in order to be able to use this, if all of these assumptions are not met, you shouldn't use this formula. You shouldn't use this method. The assumptions, number one, is that x bar is normal. Okay, we talked about why that's the case when we derived the formula. Remember, going from line 1 to line 2, we had to have that. This could happen in either of two ways. If for some reason you're able to show that you think the population's normal, you're okay. If you've got a large sample size, you're okay. Here I've got that quote-unquote magical rule of thumb, n bigger than 30, just because a lot of textbooks emphasize that. And again, I'm not exactly sure why. So we'll say, what I really should probably say here is a large sample rather than just saying n bigger than 30. Or if you have both of those, you're great as well. You also have to have your data from a simple random sample, and you also have to know sigma. Sigma shows up in the formula, so it's logical to expect that you would have to know what it is. Okay, so let's do an example. All right, so this one, a sample of size 23 is taken from a normal population with standard deviation 2.6. The mean is found to be 14.2. Okay. So number one, what is our point estimate from U? Remember I said point estimates are really easy to get? And on most of these, like homework problems and stuff like that, I'm going to ask for what the point estimate is. If you think too hard about what the point estimate is, if you're doing some long, elaborate calculations, you're probably doing it wrong. The point estimate, you should just be able to look at the problem and write down what it is. Right? So we take a sample of size 23. So what is the 23? What does that represent? Sample size, not the population size, the sample size. So how do we denote that? Heard somebody say S is the sample standard deviation. N. So N is 23. This is something I would highly recommend. Somebody the other day was saying, I tend to have trouble doing kind of word problems. Here on out, that's all we're doing. Every single problem we're going to do is going to have at least something of a context to it. This is an example of a problem that probably has the least amount of context to it, because I didn't really describe what the population is or anything like that. So what I would encourage you to do first is go through, identify, well, what's N? Okay, well, N is 23. It says we take a sample of size 23 from a normal population with standard deviation 2.6. I said the population has standard deviation 2.6. The population has standard deviation 2.6. So what is the 2.6? Sigma. Right? Because I'm saying it about the population. The population has standard deviation 2.6. So I'm telling you sigma. So that's what this 2.6 is. So are we okay with that? Okay, so we take this sample, and then we find out the mean is 14.2. Does this 14.2 really represent everything in the population? Because remember, the first sentence says we took a sample, and then we found out the mean was 14.2. That's x bar. That's x bar. Another good reason, or kind of something to think about, is if we knew what mu is, why would we do a confidence interval for it?
Right.
Okay, so I'm probably never going to tell you what mu is. Okay, so what's the point estimate for mu? Remember, the idea is, over here in this population, you've got some big population where mu is the actual average of all the values in the population. We took a sample. What statistic over here in the sample is going to give us a point estimate for mu? X bar. So the point estimate for mu is just x bar, which is 14.2. So somebody put a gun to your head and said, what's your best guess for what mu is? You'd say, well, it may not be right, but my best guess is 14.2. What's that?
High stakes.
Yeah, high stakes, right. Okay, number 2. What if we want to get a 90% confidence interval from mu? So let me do this on a different piece of paper here. Okay, so we already said n is 23. X bar is 14.2. And sigma is 2.6, right? Sigma squared. Sigma is 2.6. And we want to do a 90% confidence interval. For right now, I'll just give you a couple of these. Probably the most common confidence levels . The most common one are 90, 95, and 99% confidence levels. Those are the ones that people use most frequently. 95, we've already talked about. What's the Z critical value associated with that?
1.96.
That's the 1.96. 90%, we actually looked at that one too. Remember we said the middle 90% of the area was 1.645. And then for 99%, 2.576. So for right now, just write those down. Later on, they're actually going to be on a table that I'll pass out. For right now, just we'll keep those in mind. So if we're going to do a 90% confidence interval, we're going to do a 90% confidence interval. It's going to be x bar plus or minus the Z critical value times sigma over the root n. Now, in the homework, sometimes I'll ask for things called the margin of error. When you do a confidence interval, you guys have probably heard of margin of error before, right? Like when people do political polls, right? Like they'll say the margin of error is plus or minus 2.5 percentage points or something like that. That's literally what it is. And so when we talk about proportions, we'll actually mention that kind of in that context. But for right now, the margin of error is literally just this thing that you add and subtract. So if I ask, tell me what the margin of error is, that's what this piece right here is. That's the margin of error. This thing in the sigma over root n, that's the standard error. I probably won't ask for that as much. But the thing, if I say, what's the margin of error? The margin of error is literally the thing you add and subtract. So maybe we'll calculate that separately just in case that's something that we want to know. So for our case, x bar is 14.2, plus or minus, what Z critical value should I use here? We're doing 99%, or did I say 90?
90.
I said 90, okay. So 90%, so we'll use 1.645. Sigma, we know that to be 2.6. And then we're going to divide by the square root of n, and n is 23. And so we would just use our calculator. Maybe for some reason we want to know what the margin of error is first. Let's do that. So I'll take 1.645 times 2.6 divided by the square root of 23. And so that's 8918. So all I did was I just calculated this piece first for whatever reason, and that's the margin of error. So if I said, what's the margin of error? You'd say, oh, the margin of error is 0.8918. So that's easy enough. And then to actually get the confidence interval, we do it once with subtraction, once with the addition. And so it's 13.3082. Up to 15.0918. All right, so this is our 90% confidence interval for mu. We think mu is somewhere between 13.3 and 15.1 or 15.09, something like that. Okay? Any questions on that? Okay? Go back to the other slide. So that's our 90% confidence interval for mu. Number 3 says show that you check the proper assumptions. Are we okay in terms of assumptions? There's 3 things, 3 assumptions we have to check, right? So, assumptions. The first assumption is what? We don't have to know the population's normal. Here, although here we do.
X bar.
X bar is normal. So is X bar normal? The answer is yes, because the population's normal. Right? So it doesn't matter how big the sample size is. Probably 23 is relatively big anyway. Number 2. Was SRS the next one I had? Did I say that in the problem? I just said a sample of 23 is taken. I should have said a simple random sample. So let's pretend that I said. Let's go back. We can modify this. And a lot of these I should have said SRS. There we go. It says SRS now. Yeah. In reality, you can't do that. If somebody's taken something that's not a simple random sample, you just kind of you have to do something else possibly. All right, and number 3, sigma known. Yeah, that was given, wasn't it? So sigma known, yep, that was given. Okay, so assumptions were good. Number 4. Number 4 says, is it reasonable to think that mu is 13? So what we're doing here is we're saying, like, for some reason, some expert or somebody says, okay, well, we think mu is 13. Does our interval support that claim? Well, what I would encourage you to do for this part of it is just to kind of draw the number line. Right? So here's the number line. Our confidence interval goes from 13.3082 up to 15.0918. So maybe that's what this is. So this is 15.0918, and this is 13.3082. Okay? And the claim value, that's what this is right here. This is people sometimes call this mu claim. Because somebody's claiming that's what mu is. So mu claim is 13, that's right here. My drawing's not to scale, by the way. Yeah, all we have to do is check to see, is the claim value within the interval, in which case it would be reasonable. If your claim value is outside the interval, it's not reasonable. So what would our decision be? No, it's not reasonable to think that mu is 13.
So do we have to show that?
No, but what you have to do is this. If we think it's not reasonable, the next logical question is, well, how different do we think that it is, right? We have to do some subtraction here. So what we'll do is we say, okay, well, we think it's different by at least this much. Now, it could be more, but we think it's different by at least that much. This thing right here, this distance, we call MVD, minimum verifiable difference, MVD. The MVD is literally just the difference between the claimed value and the closest endpoint of the interval. And it's a distance, so it's always going to be positive. So in this case, the MVD is just 13.3082 minus 13, which is 0.3082. Right? So putting all this together, what we would say is, do we think that it's reasonable to think that mu is 13? The answer is no. It's not reasonable based on our results. And if not, how different do we think it is? Well, we think it's different by this amount here. And again, my drawing's not to scale. But that difference comes out to be 0.3082. So we think, is it different than 13? Yes. How different do we think it is? Well, we think it's different by at least 0.3082 units, whatever we're talking about here. Okay? Any questions on this example? We're okay with this? Hopefully you'll find, I think this material in this unit's slightly easier and slightly more understandable and relatable than the stuff in the probability unit.